Good morning, Year 11 Extension. Our next topic we're looking at now is another calculus topic, so we're looking at some rates of change. And today's heading is also rates of change. So I want to introduce you to displacement, velocity, and acceleration. These may be familiar to you if you do physics, but it doesn't matter if you don't. So when we talk about the displacement of something, whether it's an object, a car, a particle, anything, we talk about where it is, okay, the position of it. When we talk about the velocity, it's how fast it's traveling, which we can call the speed. And then when we talk about acceleration, it's the rate that your speed's changing. So I just think about if this was you in a car, your displacement is where you are in the car, so whether you're at home, whether at school. The velocity, well, we know that's our speed that the car's going to be traveling. Okay, so how fast did you travel in your car? And then the acceleration, well, we know we have an acceleration pedal, and that pedal, it controls how our speed can increase. Okay, so it's the rate that our speed changes. Now, when we relate it back to maths, we represent x. So instead of using y equals, they are now using, with these motions, they use x equals. More importantly, they use x by itself for displacement, x dot. So instead of doing dashes, we're doing dots now for velocity, and x double dot for the acceleration. But think about it using calculus, what we know so far. F of t, so we're using t for time instead of x now. Alright, so the function in terms of time, because when we're relating these questions to motion, we're applying them to real life, so we're talking about time. So the velocity can be found by taking the derivative of the displacement. And then acceleration can be found by taking the derivative of velocity, or the second derivative of displacement. So that's it. That's how the calculus applies. We find each one by differentiating the one before. So what's going to happen in year 12 is when we learn how to integrate, which is going backwards, we can then go jumping back up in the other direction. If we're given acceleration, we can go back to velocity. But for now, for year 11, we can find velocity or acceleration if we are given displacement. Okay. So let's have a look at some other important notes. So I like to talk about definitions when we're introducing this idea, because it can be a bit confusing, the terminology they use. So when we talk about something at rest, let's think about if your car is at rest. Think about whether, and if I was in person with you, I would say, what do you think that means? Does that mean the displacement would be 0? The velocity would be 0? Or the acceleration would be 0? If your car is completely at rest, think to yourself right now, what one of those would be 0? So, hopefully, you worked out, or you thought it's going to be the velocity that is equal to 0. Okay, the reason is because if you're at rest, you have a 0 speed. Okay, you can be at rest, think about it this way, you can be at rest at a traffic light. Okay, so your displacement's not 0 because you're not at home. Okay, you're out and about still, so you have a displacement, but you're still at rest. So it doesn't mean when displacement's 0. And the same thing with acceleration. You could sit in your car, not be moving, and push your accelerator pedal. So you can have an acceleration still when you're at rest. So that when we talk about some object being at rest, we're talking about the velocity being 0. Okay, otherwise represented as x dot equals 0. Sorry, my stylus is playing up, so I'm just trying to use my finger instead, which is a bit messier. Okay, alright, The next one, well, this one is what the whole topic's about. If we hear rate of change, straight away, as soon as you see that word, think of the derivative. Okay? So if we need to find a rate of change of something, we find the derivative of that something. Okay? Initially, if I said to you, initially, there were this much happening, it would mean where time is 0. Okay, so time equals 0, or t, we represent in this topic, equals 0. Now, if the object is at the origin, okay, that is where the displacement is equal to 0. Now, something important to note. If I have a graph of some, let's go, you driving, going for a drive. You start at the origin, the axis, origin. You drive, turn around, and come back. That's how we would represent it. T for time, and then this would be x because it's the displacement. So what we call the origin is when our displacement is 0. This is where it gets confusing because now we represent the y-axis with x, because x is our displacement, how far you're traveling. So when you're at the origin, that's where you're at your t-intercepts. Okay? It's confusing because in the past, when we say origin, we would think it's the origin. It's the x and y being 0, the point 0, 0. But it's not just that. Now when we talk about something being at the origin, it just means it's back where it originated, okay? Back at the same spot it originated, which is where it comes back down and returns back down here. So if you had to find when something is at the origin, you would find the t-intercepts, okay? Alright, so now let's have a look at, I've got 2 HSC example questions here. Here's our first one. Alright, we've got particles moving on the x-axis. It is initially at the origin. Its velocity is v meters per second and time is t seconds, and here's our equation. So let's have a look and think about what it's told us here. Initially it's at the origin. Based on my definitions, that means initially, well, I know initially means when t equals 0. And if something's at the origin, that means x, the displacement. Now what they're doing here, they've said v equals. That's the exact same thing as x dot or f dash of t. So I'm just going to use d and keep their pattern going, using d for displacement rather than x. D, that is not a d, let's go. The displacement is equal to 0. Okay, so that's what that underlined piece of information tells me right there. And here we've got an equation for its velocity. It says, what is the initial velocity of the particle? We'll say, okay, well, if I need to find the initial velocity of the particle, that's where, well, what do I know? Where time equals 0. So what I'm going to do is I'm going to substitute in t equals 0 into the equation. And then my answer is going to be the initial velocity. So subbing in t equals 0 in my equation, I get v equals 0 over 16 plus 0, which gives me 0. Now it's a worded question, so I would definitely write a worded answer and say, therefore, the initial velocity of the particle is 0 and we're in meters per second. So make sure you put meters per second in your answer. But worded question, do your worded answer. Alright, so now part 2 says find an expression for the acceleration of the particle. So now we think, okay, we're given the velocity. What do I know? When I have velocity and I need to find acceleration, I differentiate. So you have to differentiate that function. So you've got to pull back out all of that information you know about differentiating something. And just think to yourself before I tell you, how would I differentiate that equation? Anybody? Well, hopefully somebody shouted out to their screen, product rule or quotient rule. Okay, either one will work depending on how you go about it. But if it's a fraction, we'll go with the quotient rule. So differentiating, when we have a t on the top and the bottom of the fraction, we do the quotient rule, which is our v u dash minus u v dash all over v squared. Okay, give that a go. I will too. Okay, so I've cheated because my stylus is just playing up badly, but hopefully when you found your u dash, v dash, subbed it all in, you get an equation. So they've just gathered like terms and factorized to get their final answer there. And there's an expression for the acceleration. So now, the last part says, okay, find the time when the acceleration of the particle is 0. So think about what that means. What you've just created is an expression for the acceleration. So what we need to do on this second part is find a t value when a is equal to 0. So what you're going to be solving is this equation for t. But, good news, I'm solving it equal to 0. So what you're solving is everything equal to 0. So when you bring the entire denominator over, it's going to cancel everything out. Okay, so there's going to be 0 timesing by that denominator, which will just give you 0. So then solving that denominator, you'll end up with t is plus or minus 4. So what you actually get there is that t is equal to plus or minus 4, but because t represents time, you can't have a negative time. So therefore, t is equal to 4. Okay. Alright, I want you to have a go at this next example now. We'll talk through it together, but if you'd like to pause the video here and give it a go on your own, you can. So this was another past paper question. Pause the video if you want to give it a go on your own. Okay, I'll assume you've given that a go. So part 1 says how much water was initially in the tank. Initially, well, what do I know? Initially means when time is equal to 0. So all you will be doing for the first example is substituting 0 in where t is and solving that. Okay, so you end up with 50 litres. Okay, and again, I would write therefore initially the tank has 50 litres of water. Alright, part 2 then says after how many seconds was tank 1 quarter full. Okay, so how many seconds, so that's solving for t, was the tank 1 quarter full. So what you're going to be doing is solving it equal to a quarter, and you need to find t. So it'll be an equation you have to solve. So your first line will look like this, because we know that it initially has 50 litres in it. Okay, so that's why we've got equal to 50 on 4, because what they've done there is that we're finding a quarter of 50. Okay, so a quarter full is a quarter of 50, which then gives you just 50 on 4. Or you could have just had it as 12.5. But that's why they've got it equal to 50 on 4. And solving that equation all the way down gives you an answer of what's going on? 40 seconds. Okay, so have a look at how it solved it. When they divided the 50, it cancelled nicely to just a quarter again. Then they square rooted, and then minusing the 1 Flipping the negative around, timesing by 80 will give you an answer of 40 seconds. Again, I would definitely be putting a therefore statement. Okay, so exercises for today. Have a go at exercise 8.12 and those questions there. Please make sure you post in Teams if you have any questions, and I'll get back to you.